Something that I like to do when I'm learning a new function that I don't know much about is come up with a really basic version of that function and type it into Desmos and start playing around with it. So here I've got the most basic possible exponential function. F of x is equal to b to the x power. And so here I have a slider for b, and I can play around with b and see how this changes everything. So first thing I notice as I move b around is that it kind of pivots. It kind of like has this weird flex happening in this area, and it's happening where it pivots around this 0.01. And like, well, I wonder why that is. So if I think about it, right, x is the variable I'm plugging in here. So if I were to plug in 0, I would be taking some power, some base b to the power of 0. Well, we know that anything to the 0th power is 1. So it makes sense then that this 0.01 should be on every exponential graph, on the graph of every exponential function, provided there's not been transformations to move that point. But if we just have the standard form of b to the x power, then at that point we'll always be on it. So that's interesting. No matter what b is, at that point we'll always be on it. We can also see that as we increase b, this kind of gets like steeper. So it kind of like gets steeper and steeper, which makes sense too. Because if I wanted to know, like for example, what is f of 2, well, that's basically saying, all right, 2 goes into the x, so I take 8.5 and I'm squaring it. So well, let's do 8. That's a number that's easier, right? That would be 64. I know that that would be 64. If I change this to like 5, well, that's 32,768 already. And so if I were, for example, if I wanted to like graph the point 5 comma whatever f of 5 is, that is going to change a lot depending on my base. So if I go down a bit, if I go down to like a number that's reasonable, like 1.5, 1.5 to the 5th power apparently is 7.5937, and that's on that graph. But if I zoom out a little bit and then just change this, you can see how fast that black dot just takes off, right? Because I'm doing this, and this is a property of exponential functions, that they grow extremely quickly, or they get larger very, very fast. We can also sort of play around with this. So what happens if we get smaller x value, a smaller base value? So if we have a smaller base, right, it's flattening out, it's flattening out, it's flattening out, and then 1 is just a straight line. Okay, so why is that? Well, b is the base, and so if 1 is being raised to any power, it's going to be 1, right? 1 to the third is just 1. 1 to the sixth is just 1. And so that makes sense then. So this doesn't really do much for us. It's just a line. It might as well be y equals 1. Okay, so that's interesting. What if I go less than 1? Ooh, it like now it's getting going from smaller from larger to smaller. So what if I like put it at zero point 0.5? Does this make sense? Well, zero point 0.5 to the 0th power is 1. Zero point 0.5 to the negative first power is 1, so it's 0.5 is 1 half, right? To the negative first power, that'd just be positive 2. 0.5 to the first power is 0.5. 1 half to the second power is 1/4. 1 half to the third power is 1/8. So this makes sense. It's getting smaller and smaller and smaller and smaller and smaller. And if I made it even smaller, it's just going to get very, very small, very, very fast. So like really small number of 0.1, that would like get that already be 0.01 as squared, right? 1/10 would be 1/100th. This would be 1/1000. This is 1/10,000. This is 100,000. This is already so small that Desmos rounds it to 0. And then what happens if I go negative? Well, that's 0, so 0 to any power 0. And then, ooh, so that's also right. 0 doesn't make any use to us. But then I go negative, the whole thing just completely disappears. And does that make sense? So if we just think about this logically, right? If I took -2, like that's a base, and I raised it to the first power, that's -2. If I took -2 and I raised that to the second power, that's -4. Actually, so it's not that, right? It's negative. So that's +4. If I took -2 and I raised it to the third power, that's -8. So let's like plot these values. Well, let's do one more. -2 to the fourth power. Okay, so let's plot these. These are going to be my x values are 2, 3, and 4. My y values are going to be 4, -8, and 18. So if we plot them on a table here, we can say, oop, that didn't work. Plot them on a table. We can say, okay, so we had 1, 2, 3, and 4, and the y values that came out were -2, 4, -8 and 16. And you can already see that this is not going to be good, especially because if I just chose integers here, what if I chose like 0.5 to the -2 power? Oh, sorry, I didn't do that, right? If I took -2 to the 0.5 power, to the 0.5 power. Well, that's the square root of -2, and we can't do that. That's not a real number output. So what this means is this is not even continuous. This is not a function. So that must be a limitation to our exponential functions. In fact, it is. We can't have negative bases. Hey, one other thing I want to show you really quick to add relevance to all of this. Ever since we started this coronavirus thing, I've been plotting data that I've been collecting off the Johns Hopkins website. And that data is on this table here, and you can go on the website and find it yourself. But what I've done is, when I first started doing this, I wanted to see is the growth exponential, and you can see actually that, and I set it up this way here. If you look at this A represents like the percent growth. So the base here in this case is representing the growth rate, and that's always going to be greater than 100 if something is growing. So I mean greater than 1 if something's growing. You just saw on the previous slide, right? If I had values greater than 1, it's going to be increasing. Okay, so in this case, I wanted to know what A was specifically, and I could toggle that. They were saying at first that it was about 22%. And so when you type in 22%, you see that something happens there. So we can actually adjust B to sort of set that out. And it actually followed it pretty well. So then I started tweaking it and changing it around and seeing, oh, okay, that's pretty close, right? We're trying to make the black line here match up with the green dots. And so this ends up being pretty close, and it was very much an exponential growth function for a while. But if it still was exponential, we'd be in a lot worse shape than we are now. In fact, we have to zoom out really far to see where the x values would line up here, to be way up here. Now, that's not to say that what's going on right now is not bad. We're at the latest count, is almost 825,000 confirmed cases. This is total cumulative cases. This isn't taking away those people who have recovered from it. It's just the data from the website. So what you can then start doing is messing with a regression. So we can try to use let the computer match the data the best it can, and it doesn't do a very good job here. And the reason for that is we have all this other data here that it's trying to match up to, and an exponential function is simply not versatile enough to match the data. And so what you can start doing is playing around with other types of functions. And this R value, and this R squared is really a good way to measure how closely correlated your regression is to the data. And this is high, but it's not that good. So how can we do better? Well, there's another kind of regression we could do called a logistic regression. And a logistic regression is actually much more characteristic of what we see in nature when you talk about the growth of things. They can only reach a certain maximum amount. There's something called a carrying capacity, which restricts growth at a certain amount, where it starts off exponential, but then it flattens out. And so ultimately, when they start talking about flattened curves, is when you're incorporating something called, or when you're looking at something called a logistic growth. And you can see that actually this is a very good R value. This is obviously not accurate. We're still kind of going up pretty fast here, but it's anyway. Hopefully, something fairly a little bit encouraging for you when you start thinking about exponential functions and exponential growth, which is what we're going to be talking about here for a little bit. To quickly summarize what we just talked about, an exponential function is an exponential function when the base b is greater than 0. Okay, so it has to be greater than 0. We saw when we had a negative base that it went all over the place. We had this non-continuous relation, which is not a function. Okay, we also saw that when b was 0, when b was 1, we just had a straight line. So that's not relevant. That's not an exponential function. It's just a straight line. And so f of x is equal to b the x. That's an exponential function. And then there are some common bases. I didn't really show you those, but the common bases are 2, 10, and e. That's certainly not to suggest they're the only bases, but they are ones that come up quite a lot. When we have 2 raised to different powers, this is like a base 2 thing. That's 2. It's very common for us to know what like 2 squared is 4, 2 to the third is 8. It's like 2, 4, 8, 64. 2, 4, 8, 16, 32, 64. What's the next one? 128, 256, 5. What's the next two? 256, 512, 1024, and 2048, etc. There's even a game about this one. And then 10 to different powers. This is really comfortable for us because we talk about base 10. And then this E one, which we might not be familiar with, comes up a lot, and we'll be talking a lot about that in the future. Okay, here is the graph of what f of x equal to the x looks like. This makes sense, right? These numbers are all pretty natural for us to understand. You can see that if we add in the graph of f of x equal 10 to the x, it's a very similar looking graph. It still has that same point in common, but that it increases at a faster rate here. And then E, okay, E is about 2.718. Okay, so it's going to be a graph that's steeper than 2 to the x, but not nearly as steep as 10 to the x. And you can see the orange graph here is the graph of E to the x, so it kind of splits the difference between the two. But again, still has that same point of 0, 1. One last thing to consider here is that an exponential function is just like any other function. So when we can apply transformations to a function, we can do the same thing for exponential functions, and they look the same. They do the same thing. So here we have, starting with the graph of f of x equal to the x, and if we have these changes, like this -1 is we're subtracting from the input, so that's going to be a horizontal translation of 1 to the right. We have this multiplying everything by -1, which is going to result in a vertical flip, and then this 2, which is a shift of 2 up. So what we can do is we can take a point that we know on f of x is equal to the x, for example 0, 1, that's always a good point to choose, and we can move it over 1, right? That's going to end up being right there. So basically everything on this graph would get shifted 1 over to the right. So we have something that looks kind of like that. It's bad drawing, but that's essentially takes care of just that translation of -1. Okay, now this negative, this flip here, means we're going to have to flip everything. So everything that was above the x-axis is going to be below the x-axis. So it would actually be, this point here would then get mirrored across the x-axis to down here. So now the graph would look something like this. Okay, it's just a flip like that. Let's delete the old one. Okay, and then finally, this shift of 2 up means I'm going to put these back up to 2. So I'm actually back to that other point that I was at. But all these points will get moved up by 2. So now we're dealing with something like this. So it would be up here, and then it would come down and do something like this. Okay, so it's not super. That's not super accurate, but I do know for sure this one point on the graph here, 1, 1 is definitely on the graph of this function. We can check that, right? What is f of 1? Well, f of 1 would be, so we have -2, it's -2 to the power of 1 minus 1, right? Plus 2. So 1 minus 1 is 0, so this is -1, right? 2 to anything to the 0th power is 1, so that's -1 plus 2, that's just 1. So yeah, the point 1, 1 is definitely on that graph. And that's just something to think about when it comes to graphing exponential functions, is that we can just apply transformations if we know the parent or the most basic possible version of the function to start with.